When you have an object that's moving, it can collide with other objects and cause them to start to move. This implies that there's some sort of energy associated with motion. We call that type of energy kinetic energy. If you have a mass with mass m moving with velocity v, the amount of kinetic energy it has that it can impart to other bodies is equal to 1/2 mv squared. This is true for classical physics. If you care about relativistic stuff with Einstein, go ahead and move on to that. For us, we're going to stick with this classical definition, 1/2 mv squared. This energy then, we can look at the units of it, and it has units of mass times velocity squared. In SI units, that would be a kilogram times a meters per second squared, or meter squared per second squared. We can combine those as kilogram meters per second squared times meters, which is a Newton meter, or a joule. This implies, or doesn't imply, actually states, that kinetic energy has the same units with work. And in the work energy principle, we'll look at how those are related. For now, this is a fine definition. It works well. It describes some behavior. I'll just add one more thing, how this relates to linear momentum. Specifically that because linear momentum is defined as mass times velocity, you can say that my velocity is equal to linear momentum over mass. We can substitute that into our kinetic energy statement and say that 1/2 mass times this linear momentum over mass squared, simplified, gives us an expression for kinetic energy in terms of momentum of 1/2 linear momentum squared over the mass. I will frequently use this one, but sometimes it might be more convenient to use this definition of kinetic energy, and so it's nice to have it around as well.